Anytime you have questions, feel free to unmute and ask, or you can type a question in chat, but feel free to unmute and use your mic. Miss Simons is going to be monitoring the chat, so she can answer questions that way as well. All right, first question we're going to do is this one. We know that there's going to be at least one free body diagram question on the exam. There always is. Usually there's multiple ones. Oftentimes there are going to be questions on a plane, on an inclined plane, like this one is. So it says a box slides down an inclined plane. As the box slides, its velocity increases. A small amount of friction, kinetic friction, acts between the surface of the box and the inclined plane. Draw a free body diagram which depicts all the forces which act on the box. All right, so let's kind of draw this thing out. Well, all right, guys, just a minute. Pen's not working. We'll figure out what's going on. Oh, I'm in Google Slides. Let me pull it up in PowerPoint. Now it should work. So let's draw a free an inclined plane like so. And we're going to call this angle of incline theta. We're going to put our little box up here. My drawing is notoriously bad, so just bear with me. Remember that when you're drawing free body diagrams, they don't want you to put components of forces in the free body diagram. You may have to draw some components to work a problem. Do that separately. Here, we're drawing the free body diagram that we're going to turn in for the free body diagram question, no components. So let's think about the actual forces that are acting on this box. One of them is the force of gravity. And we're always going to show that going straight down. And my pen is struggling tonight. So we'll draw that like so. And I'm going to label that, maybe. Struggling with the pen here. I'm going to label that mg. And I think that's the safest way typically to draw in your weight. Probably could get by with drawing a W. You might get by with drawing F sub G. When I'm doing weight, I'm going to do mg. All right, another force that we've got acting on this box is the frictional force. It tells us there's a small amount of kinetic friction. The box is sliding down the plane. We know friction always acts in the opposite direction of the motion, which means our frictional force is going to be acting up the plane like so. I'm going to label my friction as F sub F, force of friction. Can anybody tell me either by unmuting or by putting in the chat what force we're missing? If you get anything in chat, let me know, Tammy. Somebody let me know what force we're missing.
Normal force.
Normal force. And how should that be drawn in? Was that Tori that answered?
Yeah, that was me.
Tell me how you think it should be drawn in.
Perpendicular to the rand.
Exactly. So maybe something like that. And we're going to label that, and make sure you label your forces. F sub n is the best way to do that. Normal force. All right, I think that's it as far as our forces go. Again, no components. We're going to do a very similar problem on the next slide. We're going to have to use components to work the problem out. But when you're doing your free body diagram, that's what it ought to look like. Any questions on number one? All right, here's the second problem. And if you haven't done a lot of practice problems off of the real AP exam, this is what the multiple choice questions are going to look like. You're going to get very few numbers in the multiple choice section of this test. You're probably not even going to need your calculator in the multiple choice section of the test. If you do, you might need it for a question or two. This is what they're going to look like. You're going to have to manipulate equations. Essentially, you're deriving equations on lots of these problems. So let's redraw a picture here. So this says a box of mass M slides down. In this case, we've got a frictionless incline plane. The plane is angled at theta above the horizontal. Which of the following correctly represents the acceleration of the box down the plane? All right, so again, I'm going to start just like I did on the last problem. I'm going to draw in what I know. And right now, the only force acting is the force of gravity, mg. So that represents my weight. But in this case, I'm going to need to break that into components. And I'm going to break it into one component that's perpendicular to the surface. That'll be like normal force. And one that's parallel to the surface, like so. And I'm going to label that one F parallel. I'm going to label this one F perpendicular for right now. When you break it into components in this manner, when you're on an incline, if this is angle theta, this angle right here is also going to be theta. And remember that this side of my triangle, this was the weight, mg. So the net force down the plane, the net force along the plane is this parallel component of the weight. So I'm going to do a little trig and get myself an equation for that in terms of theta. Notice that F parallel is opposite theta. It's the opposite side of the triangle. So I'm going to use sine, and I'm going to say the sine of theta. Remember that sine is opposite over hypotenuse. So my opposite side is that side. And my hypotenuse of this triangle is mg. I'm going to rearrange that just a little bit for F parallel. So that's my parallel component of the weight. And that is the net force acting along the plane. So I could think of it this way. I could say F net is equal to F parallel. Well, I know F net is equal to MA. And in this case, I know that F parallel is mg sine theta. So I can cancel out the masses, same mass on both sides. And notice I've got A equals G sine theta. A lot of you probably did a lab where you derived this equation in the lab, really common incline plane lab that you do with science and motion or even smart carts along the way. But our answer here should be C. Anybody have questions on what we did on that one? You're going to see that kind of problem on the exam. So this next one is very similar. So again, incline plane, whoops. Same basic kind of setup. Here the difference is that we've got some friction. So again, I'm going to redraw this picture just to make sure we know what we're doing here. So drawing my weight, drawing a component perpendicular and a component parallel to my surface. Remembering that this is mg and that this angle right here is my angle theta, the same angle as I have right here. So again, I'm going to solve for both sides of that triangle just so we have it. We already solved for F parallel a minute ago. And the way we did that is we used sine. And we said the sine of theta was equal to the opposite side over the hypotenuse. We rearranged it to look like this. All right, for the other side, I'm going to use cosine. Because remember, cosine is adjacent over hypotenuse. So I'm going to say cosine of theta is equal to my adjacent side, F perpendicular, over my hypotenuse, mg. So if I rearrange again a little bit, I get F perpendicular equals mg cosine theta. And that perpendicular component of the weight is equal but opposite to the normal force. So that's really my normal force right there. So let's look at what it's asking me to actually come up with. Which of the following correctly represents the acceleration of the box down the plane. And it says assume that down the plane is the positive direction. So this is one where you really got to derive an equation. And where I would start is I know that my net force in this case is going to be equal to the difference between my F parallel, which is pushing the box down the plane, and my friction, which is pushing the other way. That's F sub F. So let's write it out this way. I'm going to go F net equals F parallel minus F F. All right, notice that's not going to help me much in terms of my answer choices. So I've got to do some substituting. I know that the net force is equal to MA. I just derived over here that F parallel is equal to mg sine theta. And I just derived over here my normal force. But remember that the frictional force is equal to mu times n. That's what I call the fun equation. So for FF, I'm going to need to put in mu and then the normal force, which is this, mg cosine theta. I've got mass in all my terms on both sides of the equation. So mass cancels out. And now I've got my answer. Acceleration is equal to g sine theta minus mu times g cosine theta. So looking at A. That's a little more complicated. Questions, comments? No? All right. So here we've got a problem with numbers. And like I said, you're probably not going to see a ton of questions with numbers in it. But you'll get a few. So here a 96 Newton box slides across a table. When a 65 Newton force is applied horizontally to the right on the box moves to the right at a constant velocity. How much kinetic friction acts on the box? So let's think of it this way. So we're pushing on the box, which I'll call this an applied force of an applied force of 65 newtons. The weight of the box is 96 newtons. Turns out you really don't need to know that to work this problem. Extra information. They tell us there's some friction. They don't tell us how much. That's what we're trying to figure out. Can somebody tell me what the key word in this question is that lets us work this problem? What's the most important word in this question? Maybe 2 words. Any idea? I want to tell you that those are the 2 most important words in the question. Because if there's a constant velocity, that means acceleration is 0. That also means that net force is 0. And I've essentially got a free body diagram drawn out right here. I don't have the weight or the normal force drawn in, but we know those are equal and opposite, so they don't really matter for this problem. What does matter is if I'm applying a force of 65 newtons to the right and I get no net force to the right, that means the frictional force has to be the same. So it has to be it has to be 65 newtons to the left. Or they could have written negative 65. Key part of that problem, constant velocity, zero acceleration, 0 net force. That's how you know to work that problem that way. Any questions or commentary on that one? Don't be bashful. Ask if you don't understand something. We want you to ask. That's what we're here for. All right, so here's another one. Similar problem. This time, again, 65 newtons of applied force. The box moves at a constant velocity again. What's the value of the coefficient of friction? So again, we know this time that the frictional force has to be 65 newtons because it has to balance out this applied force going to the right. So here we're just going to have to go to our fun equation. Like so. We're looking for the coefficient of friction. So if we rearrange our equation a bit, we got that. We know that this frictional force is 65 newtons. And when you're on flat ground like this, what's the normal force got to be? Somebody unmute and tell me, what's the normal force in this problem? Come on, guys. Help me out. How much normal force? Getting anything in the chat? No?
Yeah, 10 newtons.
10 newtons. Okay, not 10 newtons. When you're on a level surface like this, the normal force is going to be equal but opposite to your weight. We saw that in our free body diagram over here a minute ago, that if we had weight acting down when we're on a flat surface, the normal force has to be equal but opposite to that weight. So they gave us the weight in this problem. They told us the weight's 96 newtons. So that's going to go right here. Notice the newtons cancel out. So we're left with no units, which is what we need for a coefficient. And we just need to go 65 divided by 96. And we end up with about 0.677. So we're looking at A. Anybody have questions or commentary on number 5?
I have a comment.
Yes, ma'am.
Since we're looking at not just how to solve problems, but how to get through all the problems in the time allotted.
Exactly.
Look at your answer choices. You're asking here for the coefficient of friction, which is less than 1, which means we can automatically eliminate answer choice B and answer choice C.
Yep.
So now you're down to a 50-50 shot.
Right. And if you got to take a guess, then go with A or B, A or D rather. And that's one thing you're going to run into on the multiple choice part of the test. If you're going to run out of time, that's the part of the test you're going to run out of time on. So budget your time. You'll have more than enough time on the free response. Most people do. But the multiple choice is sort of like the ACT science section. You got to move to get through it. If you get to a problem and you realize that you're really struggling, I would say skip it. And if you have time, come back to it and deal with it later. You want to see all the problems because there's going to be some easy ones.
Yeah. You've got a little bit less than 2 minutes per question to answer everything.
Exactly. And some of them you may be able to do in, 15 or 20 seconds. But some of them, it may take you more than 2 minutes. And I would save those until the end. Come back to them. If you have time, that's great. If you don't, do make sure before time runs out that you mark an answer though. We don't want you blind guessing, but it's better to take a blind guess than have nothing written on the paper. If you're taking true, let's say you have 4 questions left and there's 30 seconds left. Pick a choice and mark it for all 4 of those. Probability you're going to get one of them right anyway. For years everybody said pick C. I don't think it matters which one you pick. Pick one, A, B, C, or D, and use it for each one. Ms. Simons, do you have what advice do you give on that?
Just be careful about the last couple of questions being you have to have 2 answer choices for physics 1, and it is all or nothing.
Yep.
But when you do pick something, when you're looking at a problem like this, you start working through it, you pick an answer, stick with your gut because it's usually correct. Unless you have definitive reason to change your answer, don't.
Yep. They're not intentionally trying to trick you. Now, they're going to give you some good distractors. They're not going to be obvious sometimes, but they're not intentionally trying to make it overly difficult. So go, like she said, go with what you think is the right answer. I think that's good advice. All right, let's move on and look at another problem then. So notice the same basic kind of setup on this one. Real simple, straightforward kinds of problems. So same box, still has a weight of 96 newtons, still applying a force of 65 newtons to the right. But this time the key word is the box accelerates. And it tells us how much it accelerates. We want to know how much kinetic friction there is. So we got to do a little bit of a derive an equation kind of thing here. Because here's what we know. The net force is going to be the difference between this applied force and this frictional force. So I'm going to say F net equals FA minus FF, like so. Now here's the deal. I know F net is MA. I know my applied force is 65 newtons. I'm looking for that kinetic friction force. And this should be a minus right here, by the way, not an equals. So let me solve that equation for FF first of all. So I'm going to add FF to both sides. And then I'm going to subtract MA from both sides. So I end up with FF equals 65 newtons minus MA. And you might be saying, well, they don't give us the mass. But they sort of do, right? They give us the weight. And we know that weight is equal to mg, which means mass equals weight divided by g. So if our weight is 96 newtons and g is 10, remember, always use 10 in physics 1. So our mass is 9.6 kilograms. So if we plug that in up here, 9.6 kilograms, and we plug in an A of 3, now we can do the math. So 9.6 times 3, that's 28.8, and subtract that from 65. And that gives us about, I must have used 10 when I came up with these answer choices, because the correct answer here, or I must have used 9.8. The correct answer, 36.2 newtons. Well, what did I do wrong there? Okay, that's right. Because we're asking for the frictional force. So 36.2 newtons to the left. Questions here. You guys really don't be bashful. Ask some questions. All right. All right, so here's another one of those where not very many numbers. You're having to derive equations again. So you apply force, F, at an angle of 60 degrees above the horizontal and to the left on a box of mass M. So let's draw it maybe something like this. And I'm going to kind of move my horizontal up here so I have something to go by. Whoops. So this is just my horizontal extended upward so I can compare my angle of my rope or whatever I'm pulling onto it. And this force is applied at 60 degrees above the horizontal and to the left. Mass of the box is M, and the force that I apply is just F, and I'm applying it like that. So let's see what we've got here. No friction acts on the system. What is the value of the horizontal acceleration of the box? So if there's no friction, that means that the net force acting horizontally is just the horizontal component of this force right here. So I'm just going to draw down a vertical like so. And I'm going to solve for the horizontal component, which I'll just call F parallel. And in this case, I'll need to use the cosine to come up with that. So actually, wait, let's hold up a minute here. Bear with me for just a second, guys. I'm missing something. What am I missing here, Tammy? Let's see.
Moving the chat window out of the way so I can see it.
Say again?
Had to move the chat window
Oh.
out of the way so I can see it. Too many screens open.
Gotcha.
So acceleration is force over mass. So you want that parallel component,
Yep.
F cosine 60, divided by the mass.
Yeah, let's see. What did I do? Yeah, I don't know what I was
because it's
thinking.
going to the left, you called that negative.
Yeah, that's what I did. I just blanked out there for a second.
Yeah.
All right. Well, you're gonna see those kinds of problems, guys. All the multiple choice look like the problems we've done so far, mostly. Very few numbers. You may have some that have some numbers and some variables. You've got to get used to deriving out equations because it's going to make you do that on most of the multiple choice questions, and then on one or two of the FRQ on top of that. All right, so here's another question. So it says a 2 kilogram block and a 3 kilogram block are attached by a rope. The two blocks sit on a flat table. Assume that no friction acts between the blocks and the table. An applied force of magnitude F to the right is applied to the 3 kilogram block. So we're pulling on this rope right here with a force of F. What is the tension in the string that connects the two masses? So we're looking for the tension in that rope. So you really got to think a little bit here to begin with. This force, since there's no friction, is the net force acting on the system. And that's going to cause the system to accelerate. We know MA. And we're talking about the system here. So let's think about the whole system to begin with, the whole thing. So this F is the force on the whole system. It's the net force on the whole system. It's acting on the mass of the whole system, which is 3 kilograms here and 2 kilograms here, which means the acceleration of the system is going to be equal to F divided by 5 kilograms, like so. Now that's the acceleration of the whole system. That's also how much each box is going to accelerate because they're attached together. This force, this tension in this rope, is the net force that acts on just this box. So now instead of thinking of the whole system, think of just box A. So for that one, F net is going to be equal to MA. The net force acting on that box is that tension because there's no friction acting on it. The mass of that box is 2 kilograms. And that box accelerates the same as the whole acceleration of the whole system, which is F over 5 kilograms. Kilograms cancel. And that means that the force of tension in that rope is going to be 2/5 times F, which is C. And again, if you hadn't seen a question like that, tricky. You've got to work from the system, and then you've got to break it up and look at specific components of that system. So be a good thing if you haven't seen problems like that before. Your teacher has access to lots of practice problems from Unit 2, and we've got a bunch of those built into the Unit 2 practice problems. You can also find several of them on AP Classroom as well. Questions on that one? All right. Well, so here's another one. So a 450 Newton box slides down a 45-degree inclined plane with a uniform acceleration of 1 meter per second squared. What net force acts down the plane? First of all, guys, what does uniform mean? What's another word for what? Somebody unmute and help me out. Uniform, another word for what? Man, you guys are a fired up audience tonight. Somebody help me out.
Constant or the same?
There you go. Constant or the same. So let's just kind of draw a picture here to begin with. Thank you, by the way, for helping me out. So here's our box. We know the weight of the box is 450 newtons. 45-degree inclined plane. It slides down with an acceleration of 1 meter per second square. What net force acts down the plane? Well, we know that the net force down the plane is equal to the mass of that box times the acceleration of that box. We really don't even need the picture to work this question out. The acceleration is 1 meter per second square. And even though they don't give us the mass, they do give us the weight. So if we just divide that weight by G, 10 meters per second square, we get a mass of 45 kilograms. So 45 times 1, and our net force is 45 newtons. And again, I must have used 9.8, but our answer should be 45 newtons. Yeah. Notice I had a mass of 45.9. So I must have been working with 9.8 there. All right, let me skip ahead for just a second, see where we're at on time. Let's look at this one. So a push mower of mass M is pushed along a flat, frictionless surface. So let's sort of draw this thing out. So let's say that's our push mower. So we're pushing it with a force of F. So if we're pushing it, we know we're pushing down and along the handle like that. The handle of the lawnmower is at a 60-degree angle with the horizontal. Something like so. The angle of the handle is then lowered to an angle of 45 degrees above the horizontal. If the same force is applied along the handle, the magnitude of the horizontal acceleration of the mower will. All right, so something we got to think about. Number one, it's frictionless. And if there were friction, this would be a bit more complicated. Frictionless surface. So the only thing that's going to matter here is that component of the force. So that being the case, what's going to happen when we lower that angle, guys? If this goes from 60 down to 45, when it's a 60-degree angle, a lot of that force is acting which way?
Down.
Yeah, vertically. So when it's 60, let's think of this component being pretty big and this component being fairly small. But when we lower it down to 45, this vertical component gets smaller. Think of it like that. And this horizontal component gets bigger. And because that horizontal component is bigger, and because there's no friction acting in the opposite direction, that's going to be the net force acting on that lawnmower horizontally, and it's going to make it accelerate faster. So when we lower the angle from 60 down to 45, the net force is going to increase, which means the horizontal acceleration is also going to increase. All right, let's go ahead and look at this one. So this is a short free response. Probably not going to look, it's not going to look exactly like a particular free response question type on the exam. But there could be a question very similar to this. 3 identical boxes, each with a mass of 0.6 kilogram, rest on a frictionless horizontal surface. What normal force acts on box B? We're on flat ground. What did we say a minute ago the normal force is equal to when you're on flat ground, guys?
The force of weight.
It's the weight. So if the mass of box B is 0.6, the weight is 0.6 times 10. So 6 newtons. That's pretty straightforward. B, if an applied force of 80 newtons is applied to the right on the rope marked F, so over here, we're applying a force of 80 newtons. What is the acceleration of box A? Well, we know that 80 newtons is the net force acting on the whole system. It's the force that's making all those boxes accelerate. So we need to work this in terms of a system to begin with. Think of it like this, where this F is the net force acting on the whole system. That's F. And then the mass is the mass of the whole system, which is 0.6 plus 0.6 plus 0.6. Each box has a mass of 0.6. So that's 1.8 kilograms of mass times acceleration. So solve that out. Our acceleration is equal to F over 1.8 kilograms. And they told us F is 80. So plug in 80 right here. And 80 divided by 1.8. 44.4 or somewhere thereabouts. That is the acceleration of the whole system, which means it's also the acceleration of A, it's the acceleration of B, it's the acceleration of C. Because they're connected. They're all going to accelerate at the same rate. questions there? All right, well, the part C then asks for what is the tension in the rope between boxes B and C. So we're looking for that. Well, we got to think that that force, because there's no friction, is the net force acting on these two boxes. So forget about C for a minute and just think of this as the system. So we're going to say F net of our system, which is now just A and B, is going to be equal to the mass of the system, which is 0.6 plus 0.6 times the acceleration. We know the acceleration. The acceleration is that. So let's plug that in. And again, we know that this F net of system is this tension. This is the net force acting on those two boxes. So 1.2 times 44.4. Uh, 53.3 or thereabouts. All right, D. Is the tension in the rope between boxes A and B higher or lower than the tension in the rope between boxes B and C? And justify your answer. Well, you could calculate it out, but that's not what they're asking you to do here. And this should be pretty straightforward, I hope. Somebody tell me their answer on D. Unmute and tell me what you think on D. Is the tension here greater than or less than the tension here?
I mean, it shouldn't be right because all the boxes weigh the same.
So you're saying it should be
The same, not higher or lower.
well, think about my logic though here though. This tension right here was the net force acting on those two boxes, right? This tension is the net force acting on what?
Box A.
Box A. And therefore it must be what? Higher, lower, same as this tension right here.
Lower.
It's got to be lower because it's acting on less mass. And we know the acceleration of all these things is the same. So for the acceleration to be the same, this tension has to be less than that tension. Whoops.
Okay, that makes sense.
Good. All right. And then finally, the free body diagram thing. Notice it says draw a free body diagram for each box. So let me clear off some space. Let's start with box A. So for box A, we know that we've got a weight acting on this thing. We're going to label that mg. We know we've got a normal force. And again, it doesn't have to be perfect, but you know that the normal force and the weight here ought to be the same. So try to draw those two arrows to be the same length. And make sure that they're going to give you a dot on the exam more than likely. Make sure your forces touch the dot and move away from the dot. And then the other thing that I need to put in here is the tension. And there's different ways you could label it. We could label it as the force of B on A. That's one way we could do it. Or maybe we could just label this rope and call this rope A, and we could call this force the tension in rope A. This is probably the best way to do it right here. Force of B on A. All right, for B, similar kind of thing. We know for B, we've got weight, mg. We got normal force. We got a force over here. We got the force of C on B. What am I missing? Somebody help me out here. What am I missing? If B pulls on A, what else has got to happen? Newton's third law, guys. If B pulls on A, what else has to happen?
A pulls on B.
A has to pull on B.
Absolutely. Yes.
There you go. Thank you. So we'll call this the force of A on B, like so. And I don't know that they would be this picky, but which one of those arrows ought to be longer? F of C on B or F of A on B? We know this thing's accelerating to the right, which I hope tells you that this arrow needs to be longer than that arrow. There's a net force acting to the right. All right, and then finally for C, same kind of thing. Weight acting down. Net force, or normal force rather, acting up. We've got this applied force just called F acting over to the right. And then again, we know C's pulling on B, which means B's also pulling on C. So we've got F of B on C going on there. So lots of free body diagram practice on that one. Anybody have questions on this particular problem? All right, so let's see where we're at on time. I think we've worked enough problems. So maybe just some last minute advice. Exams coming up soon. I'll give you some, and I'm gonna ask Ms. Simons to chime in here in a minute to give you some advice. She already told you that if you're gonna run out of time, it's gonna be on the multiple choice part of the test more than likely. So don't get bogged down on one problem. If you see a problem's taking you more than a couple of minutes, you probably ought to move on. As I said before, you want to see every problem. Don't leave anything blank. Keep up with the time. Know that, you know, if you've got a minute left or so, you've got to pick a choice and mark it. And don't forget about those questions that that require two answers, because there are is it two or four of those? Five. So the last five multiple choice, you're going to have to mark two answers. And to get the points for those questions, you've got to get both those answers right. Some of those are challenging. Some of them are easy. You want to make sure you have time to look at those questions though. But luckily those are going to come at the end anyway. So those are going to be the last questions you get to. As far as the free response go, there are some easy parts on every free response question. Make sure you get those parts. Show all your work. Each step along the way. Start out with an equation from the formula sheet if you're deriving, and work your way from that. The same sort of goes for the design and experiment question. There's always going to be one of those. I would use an equation to guide my thinking. Use that equation to guide what you need to measure. Hopefully you know how to measure it. They're probably going to ask you how you're going to measure something. If you don't know, I mean, just say you're going to use a smart cart. For most things, that'll work. There are a few things that might not work for, but for most things in physics 1, the smart cart can measure it. They're probably going to ask you for ways to reduce error on that question. What's the most common way to reduce error in an experiment, guys? You pretty much can always put this answer down on that question. What's the most common way to reduce error in an experiment?
Is it multiple trials?
Yeah, run it multiple times.
Absolutely.
Need to say that when you're talking about designing an experiment. I'm going to run this experiment 50 times, or just you can make up a number, or you could just say I'm going to run it several times. I think either would probably be okay. But that's the main way that you're going to reduce your error. Tammy, what else do you have to add as far as just last minute advice?
As far as you're allowed to bring into the exam room pencils, and I am making that a plural.
Yep.
Bring in pencils. You can use an ink pen on the free response, but I don't recommend it just because of so many diagrams and graphs and the math that we have to do.
They are going to be scanning the answers, so you want to use a dark pencil. Get a number 2 pencil, something that's dark enough that when they run that through the scanner that it's going to pick up.
So you're not allowed to use a mechanical pencil at all on any part of the test. So you can bring as many pencils as you want within reason. I have that kid in my class who says he's going to bring half his weight in pencils. Don't. But bring a couple with you, and when you get to the free response, start with a fresh pencil. And that'll make sure that your answers are actually going to show up.
Yep.
And if you want, you can bring a ruler. Now, you're not measuring anything, but they're handy for drawing straight lines and for keeping your place in the book on your answer sheet. You can use it there. You can stick the ruler in the front page of your answer booklet to find the formula sheet really easily, because you're not allowed to rip that out. Now, last year they had 2 booklets, one that had the answer sheet and the formula sheet, and another was the formula sheet and the questions. So you could always flip to the other book.
Yep.
We'll see what this year looks like. Who knows? But you can bring multiple pencils. And if you want, you can bring a ruler. If you do bring a ruler, I highly recommend a clear one so you can really see how it lines up with everything. Do keep an eye on your time on the multiple choice so that you don't run out of time before the end. On the free response, look at all 5 questions before you begin. Don't just jump straight into question number 1. Look at all 5, look at the diagrams at the top, what the pictures are. You're already going to start to formulate an idea of how you're going to solve it. Oh, this one has an incline, so it's probably going to have forces. And this one has a spring, so I'm going to do something with springs. Or this one is spinning, so probably rotation, whatever. So you already have an idea of what the question's about before you get into it. And then figure out, what are you most comfortable answering? Maybe it's not question 1. Maybe you want to jump straight to question 5. So be it. But as you do that, look and find where is the lab question, whether it's design a lab or here is a lab that you have to analyze or whatever it is. Make that your last question, because it's so easy to run out of time on just that one question and spend more than the 25 minutes that they suggest.
Yep.
Do the other 4 first, and then do the lab question last. And the lab question absolutely will be related to something on the formula sheet. So find the formula that matches whatever the lab is describing and go from there, because the formula tells you what to measure. On that free response, pay attention to the verbs. If it says derive, you have to show at least 2 steps or you do not get credit. If it says identify, you can just give an answer with no support. If it says justify and you don't put anything there, you don't get points. And that almost always follows something like a checkbox. Compare these things. Is this going to be bigger, less than, the same, or do not know? And then justify your answer. If you don't justify, you're probably not going to get points for the checkbox either.
Right.
So do both. So make sure that you're actually answering the question that's being asked. So underline the words, circle up, put a box around it, maybe off to the side. If it says, hey, find the acceleration, write A equals question mark. Just a reminder, what is it that you're really trying to find here? So that you answer that question. So if it says find the acceleration and you say 15 seconds, that doesn't make much sense.
Right. I know some students just try to use the shotgun approach to answering FRQs and just put down every possible thing they know. Don't do that. Answer the question, move on. A lot of these questions are not going to take very much at all to answer them.
No, and in fact,
Get
other
to the
than the
point.
question that says you have to answer as a paragraph response,
Right,
everything else you should be able to answer in about 3 bullet points or less.
right. So get to the point. And I would say if you're not really familiar with your formula sheet, before you take that exam,
You got a week.
that's where you ought to start studying. Become really intimately familiar with that formula sheet. Know what every formula on there is, different kinds of problems you could use that formula for. Really study that thing before you go into the exam. And if you don't have a copy of it, your teacher should be able to give you one. If not, shoot me an email and I will email you one. I'll put my email address on the screen right now. If you don't have a copy, just let me know. And I will send you a copy of that formula sheet. But that's maybe the most important thing you could do now is become familiar with that thing.
Yeah, so maybe take your copy of your formula sheet and start annotating it right off to the side. What is this one going to be used for? What is that one going to be used for? What kind of units might you have with something like this? Is this related to anything else on the formula sheet? Maybe draw a line that connects them or something like that. And then not just the formulas, but look at what else is on your formula sheet. So you've got constants on there with their units, which can help you with answering some other things. It's got the metric prefixes. You've got some basic trigonometry. So if you're having one of those days and you can't remember, is this supposed to be sine or cosine? It's there on your formula sheet, or area of a triangle. It's there for a reason.
Yep.
We use that with graphs.
Yep. There's some